Related rates, Cliff Note 2027. Just a little bit of background about some guidelines for finding answers to related rate problems. You want to take the time and kind of read through this. Okay, so we have a ladder. It's 25 feet. It's sliding down a vertical wall. We're told the constant rate at which it's sliding down the wall. And then it asks us to consider when the top of the ladder is 7 feet from the bottom, the ground, what is the rate of change of the distance between the bottom of the ladder and the wall. All right, so let's look at a diagram. Let's consider this our wall, and our ladder is maybe leaning up against the wall, something like this. So we have a right triangle. Okay, and if you remember anything about related rates, what we had to do is we had to come up with an equation that related the variables. And so in this case, it's probably going to be Pythagorean Theorem because I'm dealing with sides of that triangle. So we're actually going to end up differentiating the Pythagorean Theorem. All right, so here's the diagram. This is 25 feet. All right, and the top of this ladder right here is sliding down at a constant rate of 3 feet per minute. So that's a rate of change of y with respect to time, and it's going to be negative 3 feet per minute. All right, so when the top of the ladder is 7 feet from the bottom, when it's somewhere maybe about right here, when it's 7 feet from the ground, we want to know what is the rate of change of the horizontal component. I mean, what's the rate of change of x with respect to time? All right, so we're finding dx dt. When y is 7 feet, when the vertical distance, when this ladder has slid down to about right here, given that, well, if I'm using x and y for the sides, I'm going to go ahead and use z here. Given the ladder is 25 feet, and also given the rate of change of the vertical component. Okay. All right, the relating equation is going to be x squared plus y squared equals z squared. Now, if we think about that for just a second, z is a constant. Okay, the hypotenuse is never going to change. The two legs will change as the ladder's sliding down, but that hypotenuse is always going to be 25. If it were changing, then I'd have to put a variable there, but it's not. So find the derivative with respect to time. So I'm going to bring in the derivative operator. All right, so differentiating, t and x don't match up, so we get 2x times dx dt. All right, so we're producing the necessary notation of which we're trying to find, something. So plus the derivative here with respect to time is 2y. I need dy dt here because I've got to insert negative 3, and the derivative of 25 is 0. Notice that you can divide the whole equation by 2 if you wanted to, meaning 2 goes into all 3 of these terms. So you don't have to divide out the 2, but it just makes the problem a little less complicated. And it's convenient to divide because you have a 0, and 0 divided by 2 is just 0. So let's insert what we know and then solve for dx dt. Another option is to get dx dt by itself, since you're finding that, and then plug in values. Okay. Well, let me think about what I need to insert here. This is dx dt, that's what I'm finding. I'm just going to try this method. Okay, so x. Well, what is x? Well, let me come down here and let's look at this. And then what is y also? Well, we know y is 7. And I know the rate of change of the top of that letter is negative 3, so that's nice enough. Okay, it's the x that I need to find. Okay, well, remember, when y is 7, the hypotenuse is still 25. So I can use Pythagorean Theorem to find the missing side length x. right? So when I use Pythagorean theorem on the number 725, I'm going to get that x is 24. Okay, so now I know what to put in for the value of x. Oh, this is plus. Okay, well, I flubbed that. Plus negative 21 equals 0. Let's add a 21 and divide by 24. I guess we can simplify that. Divide out of 3, so 7/8. 7/8 feet per minute. So let's take a look at note card number 28. So this is our classic cone problem. All right, and again, here's just a reminder of a strategy for solving these problems. All right, so let's get a diagram of this cone. All right, the height of the cone is 9 centimeters. If the diameter is 6, we know the radius is 3. Okay. All right, it tells us that it's leaking water at a rate of 1 cubic centimeter per minute. So that means there's a change in volume with respect to time. So it's going to be negative 1 cubic centimeters per minute. You know, if we're dealing with volume, it's three-dimensional, so that makes sense. All right, we're supposed to find the rate at which the water level is dropping. So there's some water in here. I don't know how much is in here, but it's leaking. Okay, and this water has it has a radius. The surface of the water has a radius, and it also has some height. Okay, and what we have here is we have similar triangles. So the cone problem is that classic problem where you've got the similar triangles, you can set up a proportion. Okay, so we are actually finding the water levels dropping, so we're actually finding a change in the height with respect to time. It should be negative since the height is decreasing. And we're supposed to find that when the water that's in here is at a level of 3 centimeters. So probably somewhere down about right here. What is the rate of change in the height when that height is 3? Okay, so when h is 3 and we've got the given. And this is going to help us find the information. All right, so we're dealing with the volume of a cone. Okay, so actually before we even know that we're going to have to solve for one variable in terms of another, okay, right back up here, the relating equation is the volume of a cone. Pi r squared h divided by 3. Or just pi over 3 times r squared h. Okay. Remember, we're differentiating with respect to time, and because the radius of the water is changing as the water is leaking out, and the height of the water is changing as the water is leaking out, because both r and h are changing, we're differentiating with respect to time. We're going to have to apply the product rule. Well, no one wants to do that. No one wants to apply the product rule. So for this particular problem, because we're dealing with you know, a multiplication situation, okay, what we're going to do is we're going to get rid of either the r or the h. We're going to write one in terms of the other. So we can avoid the product rule. Okay, well, how do we do that? Well, again, we're going to use the idea of similar right triangles back up here, okay, like what we saw. I can't fit it all on the same screen, so I think I'll just kind of redraw it down here. Okay, we've got this situation. Okay, so we know this is 3, this is 9. Okay, I don't know what the radius of the water is, and I don't know what the height is. Okay, but I do know that a proportion I can set up goes like this. Well, 3 is to 9. The radius is to the height as r is to h. And when I think about when I'm finding dh dt, I don't really have any information about the radius. So I'm going to solve this equation for r in terms of h. So let's cross multiply. Divide by 9. So the radius is a third of the height. Well, yeah, that makes sense. If you wanted to, you could differentiate both sides here with respect to time. You know, there's just different things you can do. But for what we're going to do back up here is we're going to get rid of r by substituting in h over 3. So I haven't done any calculus yet. I haven't differentiated. I just want to get rid of one of these variables so I don't have to do the product rule when I'm ready to differentiate. All right, so volume equals pi over 3. Okay, r squared, r's out. R is out. We're replacing it with h over 3. Mathematically, let's square this first, PEMDAS, and clean it up. So pi over 3 times h squared over 9, square the top, square the bottom, times h over 1. Okay, let's gather up all the constant multipliers. So that's going to be pi over 27 times the variable part, h cubed. Okay, so think about what we just did. We took the volume equation, we got rid of r, and we wrote the volume equation for a cone in terms of one letter only. So now I can differentiate and not have to use product rule. All right, so I think I actually did the substitute line all together right here. So I think I'm going to move down here to where it says find the derivative and solve. All right, dv dt equals, and this is a constant multiplier, just think of the power rule. Let's multiply the 3 in front, so we're going to get 3 pi over 27. We'll clean that up to pi over 9 in a minute. Drop the exponent, multiply h and t don't match up, so multiply by dh dt. So when differentiating, if you don't introduce what you need, what you're trying to find, well then you probably didn't differentiate correctly, so that's kind of a built-in check process. All right, I think we can find what we need. dv dt is -1. I'm going to change this to pi over 9. H was 3 squared, and I'm finding dh dt. You could have cleaned up, isolated dh dt, and then plugged the numbers in, but I'm just going to go ahead and do it this way. So -1 equals, this will be 9 divided by this 9. That reduces to pi times dh dt. Divide both sides by pi, and I'm going to trade sides. So dh dt is equal to -1 over pi. Centimeters per minute. Because height is measured in centimeter, the rate is per minute. And it should be negative because the height is decreasing. So just a quick reminder about how we put our minds around related rates and what were some of the things that we needed to do. But you know, the big picture is find an equation that relates the idea, the context, the problem. Find an equation that represents that. Differentiate with respect to time, and just plug in variables. Find what you need. Plug in values for the variables and find what you need.